Robbie for that, because I'm going to say Robbie said that. I don't know if you actually did or not.
I did.
You did? Yeah, cool. So I'm going to do the top one. So if we're going to determine the oxidation state is always something to be calculated. Okay? It is never, ever, ever, ever given to you. Okay? So what I'm going to do is look at the oxidation state for every element in that top equation. Okay? So I'm going to start with the tin on the reactant side. Okay? Well, how many tins are in that unit? So that unit would be where the first symbol starts and where I now see a mathematical operation. So there's my unit. How many tins are within that unit? 1. Okay? So the number of the element times the oxidation state. Okay? Because I said we have to solve for the oxidation state, it's going to be X. Okay? What's the next element in that unit? There's no other element in that unit. Remember, we just put the box around the unit. Okay? It's all the elements up to a mathematical operator. The mathematical operator is that plus sign. So that red box has all of the elements that we want. How many other elements are in there? None. Okay? So if I add up the oxidation states for all of the individual elements, that then equals something. What does that equal?
The charge.
The overall charge. Okay? The overall charge is always given to you. Okay? That overall charge is always written in the top right-hand corner. So in this case, it is a +2. Right? And now I can go through and solve for the oxidation state. I need to get the X by itself, so I'll divide both sides by 1, and I get X equals to just plus. +2.
Sorry,
Oxidation state is equal to, I see what you're saying, yes. I use 2TO, not TWO. Right? So we know the oxidation state for that tin is a +2. Okay, so now I'll do it for the next unit. What's the next unit on the reactant side? Okay, iron. My operator's now that arrow, so I'll go through the exact same process. 1 times an unknown oxidation state equals the overall charge for that unit, which is +3. The oxidation state for iron is +3. If I go to the product side and now do the exact same thing up to my operator, okay, 1 times X equals +4, X equals +4. 1 times X equals +2, X equals +2. Okay? All of those X's are oxidation states. They're the oxidation state for the element directly above it. Okay? It is this particular reason why people get charge and oxidation state confused. Okay? Literally, faculty don't understand why we talk about oxidation state. Chemistry faculty are like, why do we talk about this? I don't understand. Okay? Isn't it the same thing as charge? No. Okay? Why do we get them confused? What is the charge on tin +2? +2. What is its oxidation state? +2. In some cases, the oxidation state and the charge are the same. That's why people get them confused. The oxidation state will only apply to a single element. Okay? And officially, really, to a single atom. Okay? But we don't even want to open that can yet. Okay? The charge will apply to a unit. That unit could be a single atom, or it could be a collection of atoms. And that's why we can sometimes get them confused, because sometimes what we're referencing as our unit is just an atom. That's why they come out the same. Okay? So now that we've identified the oxidation states, what should we do with it? Okay, well, we want to see what happened. Okay? The point of identifying oxidation states isn't to say I can do it, it's to say, did something happen to that atom in the course of the reaction? If I take a look at the tin, it went from a +2 to a +4. Okay? How does that happen?
It's oxidized.
I don't want to go with oxidized yet. Why is it a +2?
Is it lost electrons?
Okay? It's a +2 because it's missing 2 electrons. So way back in Unit 1 when we talked about basic atomic structure, we said there's protons, neutrons, and electrons. Okay? Oxidation state is the balance of the protons and electrons. Okay? So to get a charge of a +2, that means those charged subatomic particles are not in balance. That's why we're getting this unbalanced result at the end. Okay? Because I can't change the number of protons, I must be changing the number of electrons. Why can't I change the protons? That changes the element. That's what defined the element. The exact terminology we used back in Unit 1. Right? So we're changing the electrons. How do I change the electrons to get a positive value? Because electrons are negative. Okay, we have to remove things to become positive, which sounds really weird, but we're losing a negative. It's that double negative that results in a positive. Okay? That negative symbol will haunt us as we deal with calculations. We have to be very careful with it. Okay? What does it mean to be a +4? So, and I understand where you're going. There's 4 more protons than there are electrons. Technically, yes, but by making that statement, what does it sound like you've done? That you've added protons. So your statement isn't wrong, but it's the process of how you're saying it that leads to a natural conclusion that is false. Okay? So how do we get a +4? There's 4 less electrons than there are protons. Okay? We've lost electrons. The statement now becomes more difficult to deal with because we're dealing with loss and a loss of a negative, but it's more accurate to what's actually happening. And we can't misinterpret it to say, well, the protons are changing. Make sense? So tin started with missing 2 electrons, and it ends with missing 4 electrons. Which means to go from the +2 to the +4, what happened? It lost 2 electrons. That's it. Ta-da! Okay. We had this reaction long before we knew anything about protons and electrons, though. Okay. So when someone observed this, they classified this type of reaction and they gave it a name to represent this particular style. Okay. That name couldn't reference electrons because we didn't know electrons existed. So we couldn't use the loss of electrons as our name. Okay. The name that they chose to give it was oxidation. Why?
How did they know something changed if they didn't know, if electrons didn't exist?
Okay, and so this is where the second example helps us out a little bit more. If we look at those reactions, we can tell that something changed. Up here, it's hard to tell that something changed. Ultimately, we would tell something changed because we attached it to some wires and we saw a light come on, which meant electrons were transferred. Electrons that we can't see, that aren't represented in the equation, and we can't even tell that those things are charged, so how would we know? Right? So the definition of oxidation for this reaction came from better placement down in the bottom situation. When we look at, and it doesn't quite work for that one. Bollocks. Oh, here we go. I think it'll work for this one. Manganese, how many oxygens is it connected to? None. How many oxygens is it connected to? 4. We've increased the bonds to oxygen, yes? If we go through and look at its oxidation state, guess what happens? It's going to have lost electrons. So the names that we associate with these reactions, oxidation and reduction, ultimately came from the observation that these reactions happened when something reacted with oxygen. And when I increase those bonds to oxygen, I'm going to call that an oxidation because there's more oxygen there. Okay? Well, what happened to the other species? What happened to bismuth in the course of the reaction? It lost oxygen. So I reduced the bonds to oxygen. So that one gets called reduction. Once we have a concept of protons and electrons, we could then say, oh, well, this is what's happening in an oxidation reaction. This is what's happening in a reduction. And instead of us looking at it from that kind of historical context of what those reaction names were, because ultimately we didn't know anything about protons and electrons, we're looking at it at a deeper level because we now understand protons and electrons. And we have to backtrack out to that historical name. Why do we have to backtrack out to the historical name? Why do we have to use inches and centimeters? Why can't we just use inches or just centimeters?
Because we've established that type of program already.
Okay. Those unit systems have been established for long enough that nobody wants to change. Why do we have to memorize oxidation and reduction as opposed to loss of electrons and gain of electrons? No one wants to change that other system. Okay? I would argue in this case no one wants to change because it's probably easier just to say oxidation versus loss of electrons. It's easier to say reduction as opposed to gain of electrons. It's even easier to say that when I'm looking at this class of a reaction, I call it a redox reaction because it involves reduction and oxidation. Could I do that same word mashup with loss of electrons, gain of electrons? Yeah, it didn't quite work. The Lowane? It's the Lowane reaction. That's already been used. Okay? So we're holding on to that largely because people don't want to change. And I think in this case for a good reason. I could be wrong, but I think in this case it makes sense to hold on to those terms, oxidation and reduction. And Greg's been fighting to say something, so let's let him go.
I just think it's really cool just beyond just the example in chemistry, like this is one of those examples that encourage us to be critically thinking about where our language comes from and why it matters and how it changes over time. So this is when we're thinking about language in its sociocultural context. So I just think it's really cool as we deal with how people understand things, how people gain knowledge or hold on to knowledge. Like in this case, that history is one of the prime example for that larger principle that you can take into any context to enhance your critical thinking.
In English, please.
He actually gave it to you in English. Iron +3 to iron +2. What happened to it? It had to gain electrons. Okay? The +3 was missing 3 electrons. The +2 is missing 2 electrons. Okay? So to go from the +3 to the +2, it had to gain an electron. Okay? That gain of 1 electron is known as reduction. Okay? And I would argue that causes lots of confusion because when we think reduction, what happens? It gets less. And yet, what are we saying? It's gaining. Okay? The reduction term makes sense, though, if you actually look at don't call it a charge. The oxidation state. What happened to the oxidation state of iron? We went from a +3 to a +2. What did I do to the number? I reduced it. Okay?
That's what confused me at first.
It's not at first. That confuses everybody, period. So,
You think it's supposed to be the opposite.
yep, exactly. And a lot of it just comes from which angle you look at it, right? Most of what we do in chem, and I would argue Gen Chem is a little bit different, but like OChem, most of what happens in organic chemistry in particular is actually very straightforward, but you have to see it. Okay? And if you can't see it, what happens?
You failed the class.
You fail the class. Okay? Has anybody seen, they're kind of old now, so this might be back to Greg's cultural references. We'll see. Okay? The pictures where it's just this weird like static, and if you stare at it right, a 3D image pops out.
Yeah.
Yeah, cool. Has anybody looked at those and been like, I can't do this?
Yeah.
Yeah, and you're like, that's dumb. Why would anybody do this? They're just making me feel like an idiot. There's actually not a picture there. No, there's a picture there. Okay? And you can stare at it till you're blue at the face, but until you actually figure out how to actually see the image pop and twist your eyes just right, it just looks like a bunch of static. Until you get that perspective so that you can make your eyes pop the logic behind it is invisible, and it becomes challenging. Okay? Just like with those pictures, you have to continue to stare at those pictures. You don't just look at it and be like, oh, I can't get it, and now throw it away. Okay? Same thing's happening with chemistry. You can't just look at it and be like, oh, I don't get it. I'm not going to worry about it. Oh, I'm going to take a test on it. Oh, I still don't know anything about it. It's because you didn't continue to look at it. You've got to continue to look at it and work with it. Okay? You got to be screwing with your eyes. Poke one eyeball and look up, look down, move the image. Okay? You have to do that kind of interaction with the diagram to be able to get it to pop. Same thing's got to happen with chemistry. Okay? With chemistry, it's a little bit different because it's not just I'm staring at an image. You also have to use your hand, which means your brain has to engage. You have to write something down. Okay? The next layer that we have to deal with on top of this is that, of course, we add an extra term into this. What was that extra term that we ended with? The tin plus 2 caused the iron plus 3 to be reduced. Okay? Because of that, I can now refer to the tin plus 2 as a oxidizing agent. Means it's causing something else to be oxidized. Did tin cause iron to be oxidized? No, it caused iron to be reduced. So the tin was a reducing agent. Okay? Well, why would we flip that on there? Why would we put that in there? Okay? How many of you use the term you is constantly? Okay, in an everyday conversation, you'd be like, you is a cool person. No, what do you say?
You are.
You are. What are you doing when you go switch from is to are or to be?
Becoming very arrogant.
Socio-cultural.
What's the socio-culture? What are you doing to that word?
Making it proper English.
You're changing the verb. Are you actually changing the verb? You are conjugating the verb. What are we doing here when we switch from oxidation to reducing agent?
Conjugating their
You're conjugating the term. That's all it is. It's a conjugation. Unfortunately, the conjugation there is a little bit trickier because the conjugation involves bringing in the word of the opposite thing. Sorry, I didn't invent that. But all it is a verb conjugation or a word conjugation.
I feel like it seems kind of like unnecessary though, because why don't you just assume that whatever is being oxidized is reducing the other one that was being reduced?
True. But if I go through and write on a bottle for a reagent like manganese, right, I could put on the bottle, this species will be an oxidizing agent. Okay, what would that mean? That means when I put it near something, what's going to happen? A chemical reaction where that other thing gets oxidized. What if that other thing, when it's oxidized, is explosive? That might be an issue that I would want to call attention to on the manganese so that when somebody looks at it, they're like, yeah, I know this thing when it reacts, it's going to be dangerous. I'm going to call attention to the reactivity of the reagent on its own. In the reaction, you're right, it's redundant is the word. It's completely redundant in the reaction. But we aren't talking about using oxidizing agent necessarily in a reaction. We're talking about using it on a bottle, saying this is a reducing agent. Okay? And I can look at another thing that's called an oxidizing agent. Because I know when I mix reduction and oxidation together, they do a chemical reaction. What am I going to do with that reducing agent bottle and that oxidizing agent bottle? I could mix them, and what's going to happen? A big chemical reaction. So what might I do instead of mixing them?
Don't put them near each other.
Don't put them near each other. I now have a way to address safety because of the terms that I'm using. If I don't invent those terms, I would only know after the reaction happened. It's a bit late to discover that.
Worst case scenario, though.
Okay? Which is exactly the point of what you're trying to do. You now need to go through and evaluate those things and be like, well, how would those things react? If I put that acid near a base, am I going to get a chemical reaction? Yeah. Should I store those two things near each other? Probably not. Okay? So that's what you need to be thinking about, and that's where a lot of those terms come in. It's to allow us to differentiate those as a safety aspect. Okay? What I'm going to recommend is that you also go through and do that. Well, actually, before we do that. So if the iron plus 2 was a reducing agent, or sorry, the tin plus 2 is a reducing agent, what is the iron plus 3? An oxidizing agent. What is the tin plus 4? So there's our tin plus 4. And yes, this is a trick question. It's a product, that's it. It doesn't get any special terms. Why not?
It's not special anymore.
It's not doing anything. It's just the end result of these other things. Our agents are things that get applied to the reactants, not to the products. Okay? How do we know the tin plus 4 is a product and not a reactant? It's on the other side of the arrow. Okay? That's how we know it's a product versus a reactant. Okay? Questions about what's up there?
Just one small thing. So does that mean that tin plus 2 and iron plus 3 are always going to be like a reducing agent or an oxidizing agent? Like tin plus 2 is always a reducing agent then? If you're going to label it like on the bottle.
And so the labeling on the bottle is going to come down to its most common reactivity. So typically when we go through and throw in the agent terms, it's on things that are uber reactive as that species. Okay? So I could go through and reference a soda as an acid, because soda is an acid. Do we call soda acid? Why not?
Because nobody would buy it.
So one thing is a marketing aspect. Why else? When you say acid, what do you think? Danger. How dangerous is soda? Okay. Its danger level is pretty low on that scale. So when we look at labeling reducing agents and oxidizing agents, we'll call them that on the bottle when they really, really do that. Okay? In a reaction, I can reference them as reducing agents and oxidizing agent because I have the extra context of that reaction. Without the context of that reaction, maybe I would call it that. Maybe I wouldn't. Okay? It depends on its strength of reactivity.
But if you're writing in your essay any of this stuff, you should definitely be using the chemistry terminology.
Yeah. So in the essay, because it's the worst case scenario, you're pushing all the way out to this. Because you're finding that situation. What is the most extreme that it could do? Okay? So you've got 2 more equations here. I would highly encourage you to go through and evaluate just as we did for the tin and the iron, those 2 things. Okay? Unfortunately, we don't have time to do that right now, so I'm going to say you should do that on your own. If those are being like, dang, I wish I had answers to check my work. They are in the slides. And to encourage you actually getting to the slides, I'm not going to let you take a picture of it. Compound units. Okay, so now we're going to do a big shift back into our conversion systems. Okay, what are compound units? What is a unit for the speed of your car or bike?
Miles per hour.
Miles per hour. How would we write that? MPH. Does that look like a mathematical conversion factor? No. Okay. You might also see that as M/H. Okay. M's confusing, right?
Yes.
Yeah, why is M confusing? Okay, so we make that miles. H could be confusing, but a little bit less so. So we might actually add just the HR, so now we know. Okay? Does that look like a conversion factor? A little bit more. Why do we use the slash? Okay? Or let's rewrite this again as miles per hour. Which of these looks more like a conversion factor, in blue or in purple?
Purple.
Purple. Why do we write it in blue then?
To show how we got there.
It's the same thing.
Writing technologies. What was our writing technology for writing miles/hour?
Color.
Think about where it showed up.
Social norms, like
Social norms where? When you see miles/hour, where are you seeing it?
Calculator, document that you write, like typing.
In a document. Where did the document come from?
Computer.
A computer. How easy is it to write a fraction on a computer? Not very. Why do we write it as miles/hour? Because virtually everything we do is typed. It is that writing technology where we don't have the easy ability to create the fraction. So what do? We hide the fraction behind that stupid slash. Okay? Which is great for typing speed. It is horrible for comprehension on how to use the conversion factor. Okay? So if you see a miles/hours or anything slash anything else, you should immediately convert it into the conversion factor because that allows you to have something you can work with. Okay? It is that fractional system that allows you to use the system that we've already been talking about. Without that notation, you will likely make mistakes. Okay? You don't believe me? I've graded a lot of exams. You make a lot of mistakes just because of that simple switch. Okay? So, a motorcycle is traveling at 105 kilometers per hour. How far did the bike get in 120 seconds? So we're just going to skip right to that middle one. Okay? And I want it in, be a little bit obnoxious. Let's not do kilometers. Let's do miles. How could we go through and set that up?
We start with what we're trying to find. Right?
Okay, we should start with what we're trying to find. What are we trying to find? Miles. Okay, let's just be explicit right here and right now. How many of you actually wrote down equals miles before I said it? One person. What is step one in all of our conversions? Write down what you want. How many of you actually writing down what you want? Okay, less than 5% of the class. This isn't just you. This is everybody. Nobody wants to write down what they want. Okay, yet when you get in your car in the morning, do you know where you're going? Yeah? For every action you take, you know what you're doing. You know that end goal in a majority of situations. And yet when we get to solving a problem, what's the first thing you try and do? I'm going to write down what I was given. Why are you writing that down? Okay? What you're given may be entirely useless. You need to know where you're going first. Make sure you write down where you're going. Okay? What is step 2?
Write down what we're given.
Write down what we're given. Okay? What makes this question interesting? How many pieces of given information do we have? Arguably 3. Okay? It's a fun little test that we may very well see at some point in the semester. Based off of how this question is written, I can predict roughly 60% of the time, I know the first thing that you're going to write down. You know what it's going to be? Now, why did you write that down? Because it's the first thing in your list. Is kilometers miles? No. Is hours miles? Why the hell did you write the number down? Because it's the first thing that was there. Okay? That's a really bad reason to write down or start a problem. You have no reason on why to place that number except that it's the first thing you see. Okay? That's a horrible process. Does it work? Sometimes. The sometimes it works is because guess who wrote the question? Your instructor. And guess what the instructor immediately reflexes to doing? making sure they include the important information first. Why?
Trick us.
So that they don't forget to include it later on. So you as a student can almost instinctively take advantage of that and include the first thing first. Okay? What if your instructor has been thinking about, hey, maybe that's a really bad method. I'm actually teaching students to do something inherently flawed. What would your instructor potentially do? Switch the order of the information. And now what happens when you solve the question? You get it wrong. Oh, I just followed everything the way I was supposed to. No, you didn't. You just wrote down a random number and just tried to solve the rest of it. Okay? The process is only good as each rhetorical choice. If your first rhetorical choice is based off of blind luck, the rest of your choices are irrelevant. I don't care about how good the rest of your choices are. If your first one's wrong, the rest of them are also wrong. Make sense? Okay. So, is that the best thing to start with then?
No,
Why not?
because
You just lectured on it. No.
because you're beginning whatever should equal your final result.
I know I want miles, right? So what needs to show up on the left-hand side?
Miles.
Miles. So let's start with something that I know I need. Okay? 105 kilometers per hour is fantastic, but that doesn't have miles in it. Does 120 seconds have miles in it? No. How about this guy? Does that have, whoops. Does that guy have miles in it? Yeah. Where do I want the miles to show up? On top. I'm intentionally starting at this time right to left. We'll see why in a little bit. What's going to show up in the denominator?
Kilometers?
Kilometers. Why?
Because that's what we converted it to.
Because you need to divide miles or you need to show the relation between miles and kilometers.
The given information relates miles to kilometers. I can't just write miles and leave it alone. I also have to include the kilometers because the given information also includes kilometers. Right? So what I'm doing is taking that equality and saying miles over 1.61 kilometers. Why am I placing them or solving it that way as opposed to 1.61 kilometers over miles?
Because we're trying to solve for miles.
Where do I want miles to be in my answer? In the numerator. Does this second conversion place miles in the numerator? No, so that's a pretty crappy conversion to use. So what I'm doing is placing the conversion units that I've got, miles, kilometers. What number needs to go with miles? 1. What number needs to go with kilometers? 1.61. This is phenomenal as a good place to start because I now have miles exactly where I want it to be. It also sucks because I have kilometers. Do I want kilometers? No. So what needs to happen? I need to convert. Okay? This is going to be a little bit weird here. You're just going to have to work with me on this. Where do I want the kilometers to be? In the numerator. I want to write kilometers here. Why do I want the kilometers in the numerator? So that those units cancel out. So now what do I want to find in my question? I want to find the number of kilometers. Do I want any other unit tied to that? No, I want just the number of kilometers. Am I given just the number of kilometers? So we go back through the given information. I've got 120 seconds and I've got 105 kilometers per hour. Remember, we should immediately convert that into the proper system of 105 kilometers per 1 hour. So yes, kilometers as a unit shows up, but it doesn't show up by itself, which means I can't just do kilometers here. I'm going to have to put hours in the denominator. What are the numbers that go with those? 105 kilometers, 1 hour. Yeah?
Yep.
What happens to kilometers? They cancel. Fantastic. We fixed the problem. Now I've got my answer.
No, you got your hours.
Gah.
Doing a good job being vocal.
I get it,
But is everyone distracted?
Why are you not going in the middle?
We'll deal with the middle in a second here, which is going to tie back to how we initially placed this.
There's supposed to be other things in there. You know?
Right? Can this 3 cancel that 3? Why?
Because they're all on the same side of the equation. You have
3 times 6 times 1 is the same as 2 times 4 times 3, which is going to be the same as 3 times 6 times 1 over 3 times 2 times 4. Those 3's cancel. So why can I switch up the order? Multiplication, division are, it's the fancy English, or not English, math term, communicative. It doesn't matter the order in which I line those. Okay?
But did you just say math was communicative?
Greg, stay in your corner.
Don't tell Pam. That's an inside joke, don't worry about it. Okay? So cool, we fixed the kilometer issue, but I also screwed myself over because what else did I bring in?
hours.
Hours. Did I want hours in my final answer? No. So what do I want to have happen? I need hours to show up in the numerator. Okay? So I'm going to put hours in the numerator. This is where I'm going back to the middle, and I know the order looks a little weird here, but again, we'll get back to the point on why I wanted to do this. Okay? Am I given hours? Oh man, I didn't put in enough space. Am I given hours?
Yeah. You're giving seconds.
Dang it, I'm given seconds. Okay? So I won't be able to use just hours. But hours is a measure of time. What is seconds a measure of? Am I responsible for knowing how to convert hours to seconds? Specifically, no, but yes.
You go from hours to minutes.
I could go from hours to minutes. Okay? And this is the part that I screwed up. I apologize. I thought I could do it in one simple step. And then I could go from minutes into seconds, and then I could put my seconds in. What's the conversion between hours and minutes? 60 hours is 1 minute.
60 minutes. It's 1 hour.
Okay? And this is where everybody laughs and goes, ha ha ha. You really have to process this because it is very simple to switch where you place that number. Okay? 60 minutes is 1 hour. Minutes to seconds.
60 seconds.
60 seconds is
1 minute.
1 minute. So cool. This got rid of my hours. This gets rid of my minutes. Do I know the seconds? Yes, I was given 120 seconds. Do I have to do anything in the denominator for that last step? No, why not? Because in that given piece of information, 120 seconds, that's all that was there. It's just 120 seconds, which means it's over effectively 1. We could now go through, and if we looked at our units canceling out, the only thing we'd be left with is miles, and miles located in the numerator. What did I want? Miles in the numerator. So cool, now I could go through and do the mathematics behind it. Why did I insist on putting out the format like this? Number one, I completely botched and thought I had just one conversion that I had to do. I screwed up and I had to do a whole bunch. Okay? Why did I insist on leaving the 105 kilometers per hour at the beginning? Remember how we started this whole problem? What did you say you wanted to start with? Kilometers per hour. Did you want to start with it in this format? Was it 105 kilometers in the numerator and hours in the denominator? Yeah. Would you have been right? Yeah. This time. Okay? So the idea is, again, to have the logic behind why you're making the placement at those times. If you don't have that logic, the entire system can crumble. And you're relying on blind luck. Ultimately, the placement of each of these numbers and units is a 50-50. It's either in the numerator or the denominator. That's all it is. It's a 50-50 coin toss. Okay? When you go through and do homework, you're on a 50-50 coin toss that you got it right on the first try, if you trust the process after that. Okay? That's pretty good because you're now using the process, but your initial step is a 50-50. Okay? If you don't trust the process, every single one of those insertions or those conversions in there is also a 50-50. I got 1, 2, 3, 4, 5 placements that are 50-50. Does anybody know what that drops your odds to getting the question right to?
Minimal.
Yeah, it's very minimal. It's like 2.5%. Okay, of just blind luck placing those numbers in there. Okay, this is why you have to have that process. But even if you have the process of canceling those units out, your very first placement could be a 50-50. Okay, so you have to know why you're placing every single conversion, not just the ones after the initial placement. Does that make sense?
Yeah. So
Okay.
are you saying to start with what you want at the end always?
I think you should always start with what you want. Okay? One of the things that can become problematic is that requires that you have all of the given information. Okay? You were given how many pieces of information? 3. Let's box them in. There's 1, 120 seconds. There's 2, 1 mile is 1.61 kilometers, and there's 3. If you'd only used the given information, could you have gotten this question right? No. You needed to know 1 hour was 60 minutes. You needed to know 1 minute was 60 seconds. You had to pull that information from outside. Okay? There's lots of given information that you are expected to know, and you have to incorporate in. When we dealt with the conversions on that previous unit, those given pieces of information were things that you probably already knew, like 1 hour is 60 minutes, okay? And 1 minute is 60 seconds. And 1 day is 24 hours, okay? You knew those conversions. But when we move into this next unit of chapter 3, you may not know the relationship between grams and moles. But you're responsible for knowing where to find it. Okay? And that makes the next step. Okay? That next big leap is knowing where to find that information, because I'm not going to tell you it. Okay? You'll be given one piece of information, and you have to somehow turn that into an entirely different unit system. Okay? That requires that you have all those other pieces and know where to find those other pieces.
And that leads to what we talk about in writing when we say that you are supposed to, that the scientific aspect of writing is how writers discover knowledge. You have to know the process for discovering specific types of knowledge.
Kind of, sort of? Okay. So we're going to move on from that. Yeah, there's a thing there. Oh, that's exactly that. Okay. What if we wanted to get the volume of an irregularly shaped or non-shaped object? Okay. How would I get the volume of that weird starry thing?
Like just the picture itself, or like
Yeah, the picture itself.
Oh, no,
You could break it up. Okay? Come on, math people. We could be like, well, there's an oval. Sorry, that was a horrible color to pick. There's an oval in there. There's a triangle here, a triangle here, a triangle here. So I could do the area of an oval and the area of the triangle, and that would get me darn close to the actual area of that object, right? Okay? So that could work. But what if I had the crown? Okay, breaking it up would be really, really painful. I could do, and it wouldn't even be a circle. It'd be the cylinder, the area of a cylinder that only works for some parts. But then when we get all the fancy little crown things, that's not going to be easy. Okay? What about the last image? And this is a hard image to get a picture of, by the way. What am I trying to get a picture of?
Looks like a bull jumped on something. It's a tree.
It's not a tree. It is a bull. It is a bull headbutting somebody, but how is the bull headbutting somebody?
A stick.
That's not a stick. That would be a very unhappy, well, it was a very unhappy bull. Where is that?
It's coming out of its ass.
There we go. What is this?
Bullshit.
It's not.
This is the hardest time any class has ever had at decoding this image.
It's a gas.
Farting.
It's farting. How do I get the volume of a gas? How do I get the volume of an irregularly shaped object? Okay? Those volumes become much harder to measure because they're harder to contain. Okay? In the case of a gas. Okay? They aren't harder to contain in the case of a irregularly shaped solid, but gases become harder to get volumes on as well. Right? So how could we determine the volume of those objects easily? Put them in a liquid. We can measure them through displacement, like you did in the lab. We take a graduated cylinder with some water in it, and I drop the object in. The object will displace an equal volume of water. So I can look at the difference in those volumes, and ta-da! I now know the volume of the object. Okay? So experimentally, it's relatively easy to determine by using displacement. Okay? This is the whole eureka moment from Archimedes. Is it Archimedes? I don't know. Some old dead Greek dude. Okay? We can do it with a gas too, but we have to actually move it through a special system because we have to trap the gas. If the gas builds up in here, it's going to build pressure inside the system, which is going to push down on the liquid. Where does the liquid then go?
Inside the other straw.
Up the straw out into the other container. So as long as this other container has markings on it, I can measure the displacement and volume there. Okay? This is one that we have to be careful on. We will talk about it later in this unit. Okay? But gases can also take up more volume if we change temperature, say like with a candle. So we'd have to be careful in the design of our experiment to make sure what we're monitoring is the existence of more gas, not the existence of hotter gas. Okay? Which gets us to our kind of fun moment for the day, okay? Density. Okay, which weighs more, a pound of lead or a pound of feathers? Okay. So to this, we've got a link, and actually we'll record it out. I always forget to plug in the sound for this. So we'll actually try this. Kidding. Somebody actually shared that with me. One of the possible, and so it turns out that this question is actually a whole lot more involved than just science, but it's interesting enough in itself. Okay? One of the potential explanations for why people tend to screw this up is the concept of density. Okay? We think about the weight and we aren't acknowledging the density. In fact, he even called attention to it. Well, that's cheating. There's a whole lot more of it there. No, the volume is a separate thing from mass. They're two independent factors. So when we think about density, density is the relationship between the mass and the volume. And so when he said, well, it's heavier, no, what he's saying is that it is more dense. Okay? And that's the reference that he's goofing on. He doesn't quite acknowledge that. Okay? And to give you an idea, this is a really common misconception. In fact, this is one of the things that you tell little kids, and you're like, which one's heavier? You know, a pound of lead or a pound of feathers? Okay? And then you can laugh at them when they screw it up. Okay? And it makes you feel smart. It's great. Okay? The same thing is kind of happening. Okay? They don't have that comprehension of what density is. And that's a challenging thing to deal with. But it is the relationship between mass and volume. Okay? Before we get too bogged down in the formula for what density is, let's think about what it is conceptually. What is mass over volume?
How much something weighs based upon its size?
Begins with a C. 2 words. No ideas, huh?
Compound unit?
It's a compound unit, and what can we do with compound units? We can convert. It's a conversion factor. That's all density is. It allows us to convert the mass of one thing into the volume of that same thing. It's a physical property because it's inherent to that system. This is why we could take the density of gold and determine the density of an unknown sample and be like, oh, well, that's gold. And we could also open our eyes and look at it, but there's other things that look like gold too. So we could use density as a way to differentiate those. Okay? So what can we do with this? So one thing, let's think about the different phases. We've got ice, water, and water vapor. This is solid, liquid, and gas. If we look at the units for our ice and water. Solid and liquid. Typically, we see them in units of grams and milliliters. So our mass is in grams and our volume is in milliliters. Why do we pick those as our unit?
Easily convertible.
Because the IU pack or whatever sets up.
What is the density for liquid water in units of grams per milliliter?
G divided by, no?
1 gram divided by 1 centimeter cubed. What's a centimeter cubed?
Centimeter times centimeter times centimeter.
Also known as a milliliter.
Milliliter.
What is the number for the density for water? 1. It is 1 gram per milliliter. Why did we pick grams and milliliters to represent the mass and volume respectively? When I run the calculation, what do I get for a number? 1. Can the human brain wrap itself around the number 1? Yes, that's why we picked grams and milliliters. Okay? Because when I go through and use those measurement systems or those unit systems, I get a nice, easy number to work with. Okay? What happens if I say try to determine the mass for the water sample? That same volume, what would I expect the mass to be for a gas?
You would expect 1.
Should it still come in as 1? What's contributing to the mass?
The density? Or, no, the volume.
No. What's contributing to mass? The weight of what? Of water. So if I was to draw water, it might look something like this, right? There's the liquid phase of water, a little bit of space in there. What happens if I drew the gas for that? They'd be far apart. I only have so much volume to spread these in. Can I possibly put all the same amount of particles in there?
No.
What happens to the mass?
It goes down.
It goes down by how much?
Half.
A lot. Okay? A huge amount. Because when we think about the difference between solid liquids and gases, our gas has to be spread apart from each other for it to be a gas. Okay? That's the definition of it being a gas. Their particles are individually spaced very far away. Which then means I have less particles there, which then means less mass. The scale of that mass is pretty significant. Okay? It's on the order of 1,000 times less mass. Which means if I went in to try and report the mass, I'm probably getting something more like this. Is that an easy number for me to wrap my brain around? No, that's a crappy hard number to deal with. So what could I do? I could switch to scientific notation. I can kind of accept that. So your brain does well with the minus sign?
No.
Your brain does well with the powers of 10.
Yes. No.
Okay. Some people do. That's okay. Right? Does 10 to the minus 3 mean anything? Like a Greek prefix? Kind of like milli? So I could convert the unit system from being grams per milliliter to milligrams per milliliter. So I could change the unit system so that I can scale that number up into something that's more reasonable for my brain to deal with. Okay? So when we go through and look at the densities for solids, liquids, and gases, you have to be careful because the number reported will look very, very similar. But the unit will change. Look at our solids, liquids. What's the unit they're using? Grams per milliliter, grams per milliliter. What's the unit we use for gases? Grams per liter. And even then, when we scale that up significantly, we say instead of trying to look at a tiny little space, I look at a space that's 1,000 times as large, what happens to the number? That's still a really small number. Okay? But I don't have another measurement unit that I can shift to, and so I just kind of work with it. If we look at our densities, the unit systems that we picked, grams per milliliter, typically keeps the density somewhere between 0 or 1 and 20. Right? When we go through and look at our gases, if we kept them as grams per milliliter, would it be between 1 and 20? No, it would be between 0 and 0.00001. That number is too small, so I do just a unit shift so that I can scale the number up a little bit, and now it's still a really tiny number, but that tiny number gets me at least in the ballpark of 1. I can now process that a little bit. Okay? Even 0.09, you might be like, oh, that's too difficult to deal with. 9 cents. Can you deal with 9 cents?
Yes.
Yeah. Can you deal with 0.0009 cents? No. Okay, so we're at least in a place that we can do some comprehension with. Okay? So be aware of that unit system change. Okay, the next part is how do we manipulate it? Could we use this information? We've got a cylinder on the right, okay, showing 3 liquids and 3 solids. Which liquid is the most dense? The one at the bottom. L2 is the most dense. How do we know that?
Because everything else floats on top of it.
Everything floated on top of it. Why is it floating on top of it? Because it is
Less dense.
less dense. So that floating aspect has to do with density. It's the relationship between the mass and the volume. The lower on this, the more dense. Okay? The higher on this, the less dense. Okay? So which one is more dense? L1 or S1?
More dense?
More dense.
Probably S1 because it's going below.
Yeah, S1 will be more dense than L1 because it is at the bottom of L1. Yeah? Which one is more dense? S2 or L2?
L2
Why L2?
because it's below S2.
Because it's below S2. Make sense? Okay. It's probably something you've already worked with. This can get very confusing on a test because how will we present this? If you looked at the practice exam 2, you would see.
That
We'll just give it a list of substances with their densities. What's your job?
to draw a picture.
To draw a picture to organize them so that you can then rank them out according to their densities. That's it. Okay? So you're being asked to draw pictures on an exam. You should be happy, right? Like that's like what little kids get to do. They just get to open up a book and look at all the pictures. You get to do the same thing. It's awesome. You're welcome. Okay? Little kids don't get to do this part. Okay? We said density was a conversion factor. So we're responsible for being able to deal with this as a conversion factor. Okay? So if I want the density of this nugget in pounds per liter, okay? Usually what I'll get students jumping all over is, and I'll usually see this on the test, D equals M over V. And I would say, that's cool. That's neat. You could even say, well, it was written right there, but let's say it wasn't written right there, and you write that down, you go, awesome. That's what I need to solve for is density is mass over volume. Okay? That's cool. You've memorized a piece of information. You've memorized a fact. Is that fact necessary to memorize?
No.
Not at all. Complete waste of brain power. Why? What are you being asked to solve for? Step 1.
Pounds per liter.
Pounds per liter. What is pounds a measure of?
Weight.
Mass.
I'm going to pick mass instead of weight for a couple reasons. The primary reason is just being shorter. Liters?
Volume.
Volume. Just by writing down the units of what I'm being asked to solve for, what did I just write down?
Density equals mass over
Density equals mass over volume. There was no reason for me to memorize the formula density equals mass over volume. None. The question tells me that formula. Okay? It's buried in there, but if you follow the process that I'm telling you to do, you don't have to memorize more stuff. Those of you being like, Mike's telling me to memorize too much stuff. You're probably memorizing that. I'm not telling you to memorize it. Don't. Use the information from the question to help you through this. Do you guys want to take a swing at this on your own?
No.
Okay. Are we given mass or volume in the question?
Yes.
Both. We're given a gram, we're given a volume, and we're even given some conversion factors. So we've got 4 pieces of information given to us. Which of those 4 pieces do you want to work with?
The one that looks like a whole number of times.
You want the,
Okay, so I heard a reference. I want to use the 10. Okay, so immediately I'm going to freak out because what did you suggest using? The number. We do not solve with numbers. Numbers are ultimately meaningless until you associate a meaning behind them. I could start with 100. Does anybody think I should start with 100?
No,
Why not?
the number one is.
It's useless. Why is it useless?
100 what?
Exactly. If I don't know what the 100 is, it's not useful to use. I could start with my height, 6'4".
6 or 4 what?
Okay, 6'4" inches. Is that useful to use
Yeah.
in this question? Why not? What is feet and inches a measure of? Height, distance? Is mass a distance?
No.
Is volume a distance?
No.
No. You've got some of this stuff already back in your brain, and you're instinctively saying, don't use that. Stop being instinctual. Be intentional behind your choices. So let's go back and look at that 10. What is the unit associated with that 10? Centimeters cubed. Is that pounds?
No.
Is that liters? No. It is a volume, so you could potentially use it because you're doing it secondary interpretation, which you'll probably have to do in this next unit. Okay? But I would argue until we're there, let's not work so hard.
Okay.
Using centimeters cubed is not going to be a good thing to start with because
you're not trying to solve.
I'm not trying to solve for it. So pick something else. Okay? You're zeroing in on the pounds. Okay? There's this pounds value, and you added more information to that. You didn't just say pounds. You said I could use the pounds to grams, which was also extra cool because what did she not say? The numbers. Okay? Where do I want to place that pound unit?
Numerator.
Why do I want to place it in the numerator?
Because you want to keep it.
I don't quite accept that.
That's what you're trying to solve for.
Partially. Where does the pound unit show up in my answer?
In the numerator.
In the numerator. So where should my pound unit show up in my work? In the numerator. Okay, so I will place pounds there. And because she correctly already pointed out that it's tied to grams, I'm also going to include the grams there. What numbers should I place in here?
1 pound.
Ooh, can't even have me yell at you there. 1 with the pounds, 454 with the grams. Why? That's literally what the numbers are tied to in our conversion factor. Okay? So cool, we brought in pounds. Do we want pounds?
Yes.
Yes. Do we want grams?
No.
What has to happen? I need to cancel that out.
The grams need to be in the numerator.
Grams needs to be in the numerator. Am I given just grams in the question?
Yeah, 224.5.
Really? Wow, that was awfully nice. 224.50 grams. What's in the denominator?
Just 1 because you don't know.
If it's 1 because I don't know, 1 is not a don't know. What is a don't know? A question mark. 1 means you do know. When we look at that little box that has 224.50 grams in it, does it say any other unit?
No.
No. So what other unit should show up in my conversion?
No, the unit one.
No other unit. It needs to be 1. Otherwise, I'm changing the meaning of what's in that little box. Okay, cool. So what happens?
Cancel out.
The grams cancel out. That's phenomenal. I now have pounds. Hallelujah, I have my answer. Why not?
You still need liters.
I still need liters. Where do I need the liters to show up?
Denominator.
I need it to show up in the denominator. So in this next step, where do I want to place the liters? In the denominator. Am I given liters in the question? I'm not. Okay. So now we might have to rely on Madison's point out that centimeters cubed is a measure of volume, right? Do I know centimeters cubed to liters? No. I know centimeters cubed to milliliters, milliliters. Liters to milliliters, right? And with that, I also know from the given information, milliliters to centimeters cubed. And with that, I have from my given information, centimeters cubed. This says 10 centimeters cubed. Does it relate to liters?
No.
Does it relate to milliliters?
Yes.
In that box, 10.0 centimeters cubed. No. So what's in the denominator? 1. What goes next to centimeters cubed? 10. In the green conversion, what goes in there? 1 and? How'd you know that?
It's given to us.
Because it says it from the given information. What goes in the purple one? I would agree. Milli means 10 to the negative 3. The power of 10 always goes with the core unit. Okay. If we look at this, we had 5 pieces of information used to make this solve. How many of those pieces of information were you given? 4. One little piece was missing. Are you responsible for that one little piece? Yes. Okay. I don't have to memorize any kind of formulas. It's there in the solve. The units will allow me to do this. Okay. I'm not going to do more of these kind of conversions, but you can go through and test them out. Where we'll pick up on Tuesday, we'll be dealing with temperature. We still haven't gotten to moles yet. Unfortunately, we're just behind because we got to catch up in Unit 2.